ready to get started? Next. Forecasting. Forecasting. I got rid of several, especially the one we would have covered Wednesday if we didn't have a snow day, we'd be covering today, is forecasting with seasons. When a company has seasonal cycles that take place during the year with their sales, or whatever it is they want to forecast, that's the one we're skipping. It's at the end of the PowerPoint, but it's actually the most common forecasting technique used because many companies have seasons. The forecasting techniques I'm showing you is where maybe you're only forecasting a certain part of the year, or it happens to be a company that does not have seasons, but they have semi-consistent sales throughout the year. And these are all good. So we're not learning the one with seasons. Also, standard moving average is not here. So moving average, weighted moving average are so simple they take a matter of just minutes. You're going to have it. You'll know it. Exponential smoothing, great example on PowerPoint we'll talk about. Trend projection least squares is the most important forecasting technique you'll learn. Is the one that I found to be almost 90% of the time fit my data in real life the best when I had to do forecasting. And in my case, most of my forecasts were because I had to do budgets. So any accounting majors, be prepared. When you become the director of the accounting office and you have to do the budgets, you have to forecast revenue. And you need something other than pulling it out of your pants. You need something sophisticated that will look at the past and try to figure out there's a trend going on, use that to forecast the future, and then you base your whole budget on that revenue that you forecast. So that's why trend projection. This is not a forecasting technique. In the book happens to have several different equations you can use to determine if the forecasting technique is fitting the data pretty well or not. But I'm going to teach you the one that I think is the best one of the three, and because we only have time, if it were on the quiz, long pause, that this would be the only one you're quizzed on right here, called MSE, mean square error is the real name of it, MSE. Again, that's used to determine if a forecasting technique is fitting the data well, so that you can decide if that's the one you want to use to forecast the future. That's where a lot of managers make mistakes. They say, oh, I like this forecasting technique, and they use it to forecast the future. Instead, you want to first take several techniques, test it against the data, see which one works best, then use that one to forecast the future. Work with it for 6 months, test all the techniques again, forecast the next 6 months, whichever technique fits the data best. 6 months go by, test several techniques again, and so on. That's the process you should use, or your forecast will start to go awry, and it'll start not making sense because the data changes. Anytime an economic situation takes place that's odd, market crash, housing crash, we're going to have an unexpected increase in enrollment here if you're managing this university and the budget on the university, because anytime the economy starts to have troubles, people say, oh, I got laid off, I'm going back to school. I don't want this to happen again. And enrollment at almost every college increases an unusual amount. That is where these forecasting techniques may not be as accurate, because a special something happened unexpected in the economy. Could go the other direction too. Boy, this economy is going so well. Our enrollment's starting to drop because when people find it easy to find jobs, they go, why do I need to go to school? I'm making good money, I'm happy, until they get laid off. And so that's a kind of a thing you've got to take into consideration when you do your forecast. So here's the deal. No matter which technique I'm teaching you, write yourself a note that any of them, you can calculate the MSE. And most likely, you might be given a set of data and said, use these two techniques, blanky, blank, and blanky, blank, calculate the MSE, and tell me which technique would be best for this data. Everybody hear that? Because that's where this is all going. Learning how to use the techniques and learning how to test them with data so you know which one should be the best one to use for the future. Now, mean squared error, right down next to that, Whichever technique gives you the lowest MSE is the best technique. Everybody hear that? The lowest MSE means it's the best technique for that data. Let's start with something simple. I posted a couple of help web pages. Here's one right here. I'm going to put my pointer right there. First one's called moving average. Moving average can be any number of periods. You could say, hey, use a 2-period moving average to forecast. Use a 3-period moving average, 4-period, 5-period. It could be any number of periods, obviously 2 or above. Moving average. What it's trying to tell you is, however many periods the moving average technique says it is, that's the number of periods you use to add together and find the average, and then that average is the forecast for the next period. For example, underneath this heading here, on this is posted on Blackboard, it says 3-period moving average. So look at where my first forecast is, period 4. Because you have to use 3 periods that are before the period you're forecasting to do your forecast. So that 19, which is our forecast for period 4, is using the raw data here of 17 plus 21 plus 19 divided by 3. That's how that 19 came about. Now shift down. So instead of using 17, 21, and 19, shift down, and now we're using 21, 19, 23. Divide by 3 after you add them. There's our forecast for period 5, the next period after the 3 we're using. So I want to make sure you get this. This is some participation here in our last class. If I asked you to forecast period 10, what 3 numbers would you be using to find that forecast? 20 plus 18 plus 22. She looked at the 3 periods before the period I'm asking. The most common mistake, at a 3-period or 4-period moving average is, a lot of people think 17 plus 21 plus 19 divided by 3 is the forecast for where you left off, and it's not. It's for the following period. So, if we have 12 pieces of data, and I asked you for a 3-period moving average, because you can't get any forecasts for period 1, 2, or 3, you are not going to have 12 forecasts. Your first forecast can't start till period 4, so you only end up with 9 forecasts out of 12, because there's 3 periods without. Now, let's jump now to 4-period moving average. This is where you're looking at the concept. The concept is, because now that we're using 4 periods, the first forecast isn't until period 5, because you have to have at least 4 periods of data to do a forecast. So let me go over here to period 5, and it's using 4 periods, the previous 4 periods. So it's 17, 21 plus 21 plus 19 plus 23 divided by 4. That's the forecast for the following period. Shift down. 21 plus 19 plus 23 plus 18 is your forecast for the next period, period 5 or 6. And because we're using a 4-period moving average, we don't have 12 forecasts or even 9 forecasts. We only end up with 8. 6, 7, 8. Because we can't start a forecast until the 5th period. All right. You've got 12 pieces of data, and I just asked you to do on the final exam a 2-period moving average. What period is your first forecast? 3. And the only reason you need to do forecasts to compare with actual data like this is because that's exactly how MSE is calculated. You're doing as many forecasts as you can with the actual data you have, so that you can compare where the forecast would be compared to the actual data. For example, let's go back to 3-period moving average. Our first forecast was 19 in period 4. The actual in period 4 was 23, and the difference is 4. So right here, we take the difference and we square it. Let me say that again. You're trying to find a forecast to compare with actual data, so you're doing as many as you can that would make sense to line up with the actual data. Then you find the difference between, and you can subtract in either direction. You find that difference, then you square it, which means even if you subtracted one way or the other and got a negative number, Once you square it, it's going to be positive anyway. So subtract in either direction. Look at the next period on the 3-period moving average, period 5. 18 minus 21, or 21 minus 18 is 3. 3 squared is 9. See how this is going? Go ahead.
What is that 9? What is that number?
That 9 represents the amount of error that exists with this particular forecasting technique, and then it's squared. Because to calculate MSE, you're adding up the squares of all the errors you can get. And then you divide those squares by the number of forecasts that were used to get the squares. So right here, all of them added together is right there. I want you to tell me how many squares, error squares, were used to come up with that number 92. How many of them? How many? Is there 9 or 8? 9. That's right. There we go. 9 forecasts, 9 squares. There's the total. Now you divide by 9. And you found the MSE. Again, you divide by the number of forecasts being used to get the squares. And I'm really pointing this out because when we get to exponential smoothing, there's a common mistake that takes place. It's a little trickier. All right. There's the MSE for 3-period moving average. Here's 4-period moving average. Okay? Here's all, let's go to 4-period. 18 minus 20 is -2, squared is 4. 16 minus 20.25 is negative whatever, 4.25 squared. And so on and so on. We're adding the squares. We get a total of 77.1875. Do not assume that's better because it's a smaller number, because you haven't divided by, you're dividing by a different number than you did the other one. Once you do this division, now you're comparing apples to apples. Not at this point. Take this and divide by how many forecasts were used in this one. 8. 1, 2, 3, 4, 5, 6, 7, 8. Because there were 8 forecasts that we could compare to actual data. So we divide by 8. Now look at the MSEs. Now you're comparing apples to apples. Would a 3-period moving average be better with this data than a 4-period moving average, or vice versa? Which is better? 4-period. And that would be your answer. If this question would say, here's 12 pieces of data, calculate the MSE using a 3-period moving average, calculate the MSE using a 4-period moving average, and tell me which one is better. There's points on, no matter what you get here, how you interpret it. Even if you make mistakes here, how you interpret that with your recommendation as to which one's better is what it's all about, even if you're basing it on different information than what's right. Okay? Can we do moving averages, no matter what the amount of periods are? 5 periods. Just testing you to make sure. 12 pieces of data there. You're being asked to do a 6-period moving average. Your first forecast is in what period? 7. And how many will you have? You got to think of it. Okay, go ahead. How many forecasts will you have to compare?
6.
I think it's 6, because you got period 7. What, 6 period, right? You got period 7, 8, 9, 10, 11, 12. So 6 of them. And so when you get 6 squares of the error, you divide that sum by 6 to get the MSE, compare apples to apples. Okay? Moving average is done. So easy. Next, weighted moving average. Very similar. 2-period weighted moving average, 3-period weighted moving average, 4-period. Same thing, but instead of adding the data, you're going to multiply the data by the weights that are given and then add. Did you hear that? So you're not doing that division by how many at the end. Here's an example. I'm going to do, here's a 3-period weighted moving average. And the problem will say something like this. Apply 20% to the oldest piece of data and apply 50% to the newest. And then what's left? 30? And 30% to the middle piece of data. Now, you're given the percentages, you're told to do weighted moving average, and in this case, I'm trying to think of the best way to do this. just like moving average, you're actually forecasting the following period from the 3 periods you're using. So, instead of doing MSE, in this case I want to say, help me figure out if I were forecasting period, I'm going to call period 10. Think about that now. I'm doing period 10, weighted forecast, 3 periods, 20%, 50%, 30%. I know I'm going to have 0.2 times something plus 0.5 times something plus 0.3 times something. And this is going to be my forecast for period 10. Look at the raw data. My question for you is, what is right here being multiplied by 50%? Let me look at the answer. What number is right here? I hear 22 from someone. Kyle, anyone? I need a backup. 18. I hear 18 now. I need a backup for one of these.
18.
I hear 2 18s and 22. Alex, jump in. 22. And he's saying it as if, man, what are you guys talking about? How could it be anything but 22?
I got it back.
You got it back?
I thought it was middle, 50%.
That's right. 50% is the newest one. Data is always presented from oldest to newest. Did everybody hear that? Data should always be, in any forecasting, number one, always be the oldest piece of data you're working with. And however many you have, they're getting newer and newer in time to the end. So, since this is a 3-period weighted moving average, I'm asking for period 10. The 3 periods before period 10 are 9, 8, and 7. But you've got to line up 9, 8, and 7 with the appropriate weights based on the words here. Which one's the newest between 9, 8, and 7 would be 9. Period 9 has a data of 22. There's 22. This says 30% of the middle data. 9, 8, and 7. 8 would be the middle, so 8 is the 18. And then the oldest piece of data would be 3 periods back. So we got 9, 8, 7, and that's a 20. 20% times the 20, 50% times 22. I have them in different orders all. 30% times 18, add that together. That is your forecast for period 10, because we use 9, 8, and 7. Am I losing anyone? Want to see another one? See yes and yes. Okay, 2 yeses. Here we go. Let's do a 2-period weighted moving average. And I want to use 40% for the oldest piece of data and 60% for the newest. And I want to forecast period, let's forecast period 11 this time. So I know this is going to be 0.4 times something plus 0.6 times something. I just need to figure out what those 2 numbers are. I'm forecasting period 11. So what 2 periods would I be looking at? 10 and 9, very good. Which period, don't tell me the number yet, which period should 60% apply to? 10, the newest one before the one we're forecasting. So what's the data in period 10? 20, what is it, 20 or 21? 20, thank you. Here we go, and then what would 0.4 be multiplied by? 22. Whatever 0.4 times 22 is, whatever 0.6 times 20 is, you add them together. There's your 2-period weighted average forecast for period 11, the previous 2 periods. Where this is all going is, in real life, you're going, hey, I'm going to check weighted moving average with several different weights. I'm going to check just regular moving average, and maybe you're checking trend projection or exponential smoothing. And then you're finding the MSE, which, by the way, when this is on Excel, you're just changing some numbers. This is real easy once you get it set up the first time. You just keep changing them until you figure out which one for the best. You're going to calculate the MSE for every one you're testing. And whichever one has the lowest MSE is the one you want to use. So let's say this question goes on and says, here, you just tested weighted moving average with regular moving average. Whichever one has the lowest MSE, I want you to predict period 13 on that method. Now we're doing the future. So if I said you find out that weighted moving average is the best one, and that it was a 2-period weighted moving average with 40% and 60%, I'm going to set this up again because now I got to forecast the future. This is the one you're going to use, and the future is period 13. Nothing changes. I just want to make sure you're with me because now you're forecasting the future. What 2 periods should you use? 11 and 12. Very good. And what should 60% be multiplied by? I got to look. 22. Is that right? And then what should 40% be multiplied by? 15. Is that true? 40% of 15, 60% of 22, add them together. There's period 13, forecast for the future. And now we know that that's probably going to be pretty good because we checked all these techniques to come up with that future forecast.
Regardless of what period you use, do all the weights always add up to 100%?
Always. The weights will always have to add up to 100%. None of this would work. Always with weighted moving average, the weights have to add up to 100%. Or they have to add up to whatever you're using. It's not, you know.
What determines the weight?
In real life?
Yeah.
You would test all kinds of different ways. I would use, like here, a lot of times, you know, after you do, if this is your job and you're getting paid to do this, you've done this 1,000 times. And I used to always find that what fit or worked best is when I put more weight on the most recent data and less weight on the past. I tried to emphasize whatever's happening most recently, I wanted to have the biggest effect on my forecast compared to things that happened 2 years ago, 3 years ago, 4 years ago. Like I usually would use 5-period weighted moving average. And then I would test it out with different weights to make sure that my instincts of wanting to put more weight on the most recent data is accurate, or now we're fitting the data the best. And then you check how it fits. You're actually making forecasts of time periods that have passed already, so you can compare it. Once you compare it, find that error thing. You're going, oh, you know, a 5-period weighted moving average is not fitting near as well as exponential smoothing. I'm going to use exponential smoothing. And then now you start forecasting your future, you're doing your whole budget, it's all coming up with that top line, the revenue, which all your budget's based on. So, same with marketing majors, sales. So you have to go, if you're a director of the marketing department and you're going to the executive committee meeting, there's every single week sometimes, every month, depending on the company, you're bringing reports where you're forecasting what sales will be, and you hopefully are using one of these methods to determine what the future forecast of sales will be.
So you're talking about a guess and check method, but if they're not a linear program, we could write that it's just find the minimum, you know, MSE.
For one method at a time, but I don't know about every method at the same time. I wish there were shortcuts. If there is, let me know, because I don't know one, at least not off my head for sure. Okay, so we got weighted average down, pretty easy. We get something a little more challenging, right? Center, well, we have moving average and weighted average. 3-period, 3-period, 4-period, the concept's the same. Exponential smoothing. All right. Right somewhere you think you got an exponential smoothing problem. I'm sorry. Well, thanks, man. Write down to put these slide numbers down. There we go. So it goes from slide 18 to slide 23. The MSE is included on slide 23. But the actual forecasting is right there on slide 20 and 21. So, exponential smoothing is all about using what's called a smoothing constant. A smoothing constant can be any number between 0 and 1 because of the decimal. Take the decimals out. Between 0 and 100. How about that? 1 and 100. So let's say I say, hey, forecast the data, forecast it, using a smoothing constant of 0.4, which is 40. And you have to know that you have to use the opposite of whatever smoothing constant I give you to do the calculation also. So the smoothing constant and the opposite have to add up to 100 or 1.0. So if I said 0.4, what's the opposite of 40? 60. So you're going to use 0.4 and 0.6 in the calculation. If I said 0.34, you're also using what other number? 0.66, is that what it is? I don't know, right? So if I said use a smoothing constant of 0.25, The other number you're going to use in the calculation is 0.75. You're getting it. So this is where this is going. This is the raw data. 10 periods of raw data. We decided that we want to use exponential smoothing, but we're not sure what smoothing constant would fit this data best. One smoothing constant may put the weight more on the old data, and the other smoothing constant puts more weight on the ongoing forecast. So, you ready? It looks like this. Now, in this story, on this first one, because we get two examples of this, slide 20, it's using a smoothing constant of 0.1, 10, 0.1. So the opposite is 0.9 or 90. Now it's putting a lot more weight on the second part of the calculation, that 90% compared to 10%. And then you're going to see an example where it puts more weight on the beginning of the calculation instead of the end. In exponential smoothing, your first forecast is always your first actual. Look at the raw data. The first actual, again, these are in order from the oldest amount of period of time to the newest period of time. Our first forecast is always the number one period actual. There's 110 in the data. So our first forecast is 110. Now, if you wrote this down, this is the one forecasting technique that you need to write a note to that says, never use the first forecast in calculating MSE exponential only. That rule is for exponential only. E-X-P-O-N-E-N-T-I-A-L. Never use the first period forecast in the MSE calculation. Exponential only, that rule applies. All right? So this first forecast, you're just using the first actual. It's not even a real forecast. It's just so you can start your calculation. The second forecast is a real forecast. So you can base your MSE from period 2 on down. For any time exponential smoothing is being used, this rule I just told you is the exact anytime. Exponential smoothing. Never use the first forecast. The first forecast is always the first actual, and your second forecast always is the same as your first forecast. Figure that? That's a little shortcut. Here's what happens. It's the smoothing, when you're doing the forecast, and we're doing period 2, it's the smoothing constant that was given to you times the previous period's actual number. So in this case, 0.1, the smoothing constant, times 110, because the previous period's actual was 110. Then you add that to the opposite of the smoothing constant, being multiplied by the previous period's forecast. And only in the second forecast is the previous period's forecast the same as the previous period's actual. So that's why period 2's forecast is always the same as period 1. Because you're always using the same number. So now it starts to change. Here we go, forecast for period 3. The smoothing constant given to you, multiplied by the previous period's actual. So we look back at period 2, and we see the actual is 115. The opposite of the smoothing constant, multiplied by the previous period's forecast. The previous period's forecast is right there, 110. We add those up. Now we're at 110.5. Go to the next period, period 4. 0.1 times the previous period's actual. We look back at 3, and we see 125 is the previous period's actual. The opposite of 0.1 times the previous period forecast, which is right there. Notice the forecast on the previous period is always the same as the line below. This is a good way to check your work as you're going. Because here's what happens with exponential smoothing. If you make an error anywhere up here, everything from that point on is wrong. And the whole forecast is an error. Because it's all based on the previous period's forecast, which has to be accurate as you're going along. So now, I want you to help me. Again, I'm going to have to go back to the slide. If this ends up being the best forecasting technique, and I say, okay, everyone, now forecast the future, the next period. You're going, oh, there's 10 periods, right? Let's go back here. The next period will be period 11, using the same smoothing constant. Here's the concept. 0.1 times what, if we're forecasting the future? 0.1 times what number? 130, the previous period's actual, period 10's actual. Now let me go back here. Plus 0.9 times what? 115.41, the previous period's forecast. Then you add those up, you would have the future's forecast, period 11. So all of this is just to determine whether this is the technique we even want to use to forecast the future. All right, you ready? Look at this one now. The only difference between this one and the one you just saw is this time the smoothing constant is much larger, 0.8. The opposite is 0.2, 0.8, 80, 20. The same concept, you take the smoothing constant, multiply it by the previous period's actual, you take the opposite of the smoothing constant times the previous period's forecast, you add them together. Start with period 1. The forecast for the first period is always the actual for the first period. Notice it's the exact same number when we were using the other smoothing constant because period 1's actual is 110. You can't change that. Notice period 2's forecast is the exact same as period 1. I explained that in exponential smoothing, that's always the case. Now things start to change. We're forecasting period 3. Our new smoothing constant is 0.8 times the previous period actual, which was 115. Actual for period 2 was 115. And then the opposite of smoothing constant times the previous period forecast, 110. Add together, there's our new forecast, and so on and so on. I want to make sure you get this. Let's forecast period 11. Exponential smoothing constant, 0.8. Again, I go back. 0.8 times what? 130. The opposite, 0.2 times what? That's right. You looked at period 10's actual, period 10's forecast. You applied the smoothing constant and the opposite, and you've got a forecast for the future. This is so basic and easy, it's boring at this point. All right? You're going, when's it going to get challenging? You ready? Wait, before I get to the next part, let's real quick look at MSE. We took all the forecasts using the smoothing constant of 0.1 and put it right here. And we're comparing, here's the actual data. And we took all our forecasts from 0.8 and put it right here with the smoothing constant of 0.8. Notice that we don't have period 1 forecast on there because in exponential smoothing, you never use period 1 in your MSE. Find the difference. 115 minus 110 is 5 squared. 125 minus 110.5, whatever it is, squared. Blah, blah, squared. Blah, blah, squared. Let's go to this smoothing constant now. 115 minus 110 is 5 squared. 120, where are we at? 125 minus 114 is 7, or whatever it is, blah, 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 squared. 12, or 9, 12, 11. 120 minus 122.8, squared. Don't worry about which direction you subtract. Even if you get negative, when you square it, the negative's gone anyway. Now, we're going to take all of those square errors that we compared, add them together, and divide by the number of forecasts that we're using to get the MSE. We're dividing by 9 years, because we had 9 out of 10 periods. 9 here, we had 9 out of 10 periods. Look at the two MSEs. Would a 0.1 or a 0.8 smoothing constant fit this particular data better if this were our choices on what to use to forecast the future? 0.8, you did it. And if this is our choices, and I said, which one would you recommend we use in this data? You say 0.8, it has a lower MSE. It's creating less error. All right, we start the challenge, a little bit. I'm going to break this down and make it easy for you, but this is trend projection. Matt, you ready for this? This is your slope, B sub 1, and this is called your intercept, B sub 0. Sometimes this is called least squares. If you find it in web pages, sometimes it's called least squares. Sometimes it's called trend projection. But this is my favorite. In real life, I used this 1,000 times because it just kept fitting my particular data the best for some reason. Now, this looks like a crazy formula, and it's written slightly different in the text. They're the exact same formula, just set up a little differently from each other. But I'm going to break this down to make it easy. Here's what you need to do, is take the data and set it up in columns. And remember, when you set this up, it's the oldest piece of data in order to the most recent. So I'm going to jump to the example. This plumber says, I'm trying to predict how many jobs I'm going to have in December. So I load my truck up with the right quantity of materials. So the plumber said, I'm going to count the number of jobs I've had for every month for the last 9 months and see if there's a trend to help me forecast how many I'm going to have in December. Now you're going to set this up. You want to set this up and number all of your data in order from 1 to however many pieces of data you have, and you want number 1 to be the oldest. What's on top then? Which number will be number 1's piece of data? 353, it's the oldest one. And number 9 is going to be the 408. November is the most recent one in this order. And it looks like this. Number 1 through 9, there's just numbers because you put them in order. The number 1 is the oldest piece of data in order to November's number 9. Add 1 through 1 plus 2 plus 3, however many pieces of data you have. 1 plus 2 plus 3 plus 4 plus 5. In this case, we're adding all the way to 9 equals 45. Here's that data. Add them up. 3053, 387, 342. There is all the data added. Now, this next column. Stay lined up. Multiply the number of periods the data's for by the data. 1 times 353, this is called T times Y, is 353. 2 times 387, 774. 3 times 342, 1026, and so on and so on. 9 times 408, 3672. You get done with this column, add them up. Big number, 17,844. This is the sum of T times Y. This is the sum of Y. This one's the sum of T. We have one last column. Take every one of these T numbers you wrote down, 1 through however many pieces of data you have, and square them. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. 9 squared is 81. Add them. 1 plus 4 plus 9 plus 16, blah, blah, blah. This is the sum of T squared. Now, I want you to write this formula. See that 285? I'm going to show you the symbol that 285 equals. It's this little, can't remember the name of it. Sum of T, well, oh no, this is sum of T squared. T squared. That sum symbol, like that, T squared. That's what that 285 is. Let's look at that 17,000, we got to put it somewhere, fit it here. 17,844. This is equal to the sum of, what is that, T times Y. It's all this little symbol sum of means, it's adding that whole column. Just whatever that column adds up to. And you're plugging in, when you see this symbol in the formula, sum of Ty, you plug in all of those added together, 17,844. When you see in that formula, where's the other one? Sum of T squared, you just plug in 285. It's almost like you're looking at a variable, it's just written weird. Okay? I know some of you go, oh, there's some you've seen them 100 times, but there's some people that, are not, have not seen the sum of. They didn't take as many math classes maybe as others. So maybe they haven't seen the sum of. But here we go. I'm plugging in all of these totals, these 4 numbers. Plus, by the way, N is the number of pieces of data we're using to do this. How many pieces of data do we have? How many periods? 9. So N is going to be 9. You ready? N, which is 9, times sum of Ty, which is, where is it? 17,844, right? Bottom of that column. So N, N is 9 times the sum of Ty minus, this says the sum of T. You go to that first column, the total is 45. Times the sum of Y. That second column added together was 3,480. Multiply first, then subtract, you got your numerator. Now here's where people make mistakes. You've got to see the difference between t squared and t squared. The difference. This says n, which is 9 again, times. Now look at this carefully. This is the sum of t squared, which is that last column where every one of those period numbers were squared and added together. That's the 285. Minus, now this is very different. This is the sum of t squared, which is, that's the sum of t squared, but this one's different. This is trying to tell you to find that first column total, then square it. So that's why it's 45 squared. I can't tell you how many people will use 285 here and 285 here. But these are two different numbers. Let me go back to the column so you can see. This is the sum of t, and then you square it. This is the sum of t squared. So all we did was use these four numbers plus the number of pieces of periods we have. And that's all you're going to need for that slope. It just looks like a crazy formula, but really, they're just variables. You're just plugging them in. You do all the math on the numerator, you do the math on the denominator, the last step is divide, 7.4, be careful, this could be negative, but in this case it's a positive 7.4. That's the slope. The intercept, you ready? Now, the intercept says, find the mean or average of y, which is your actual data. So look at your columns again. Here's all the actual data added together, y. What do we divide by to find that average? 3,480 divided by what to find the average? 9. You have 9 periods there. Now you take that average, you got to use the mean of t, average of t. Add it up.